Hello there and welcome to Lower 6th Further Maths A-Level. This is the core part of the syllabus. We're working on the specimen paper here. Question 6 looks like this, a proof by induction question. Prove that for all n existing in the positive integers, f of n, which is n to the power 5 plus 4n, is divisible by 5. So let's break it up into its separate parts. First part, prove true for n equals 1. So f of 1 is equal to 1 to the power 5 plus 4 lots of 1, which equals 5, tick. That's definitely divisible by 5. Second part, assume true for n equals k. So therefore f of k is equal to k to the power 5 plus 4k is divisible by 5. Okay, now the more difficult part, part 3. What we have to do now is we have to prove true for f of k plus 1, which is going to be equal to k plus 1 to the power of 5 plus 4 lots of k plus 1. Okay, so this k plus 1 to the power 5, that's going to be difficult unless we expand it. I think what I'll do is I'll use the binomial expansion shortcut to expand this. So it's going to be k to the power 5 plus 5 choose 1, which is 5k to the power 4, plus 5 choose 2, which is 10k cubed, plus 5 choose 3, which is 10k squared, plus 5k, which is 5 choose 4, plus 1, and then we'll add on 4k plus 4. Okay, let's split up the bit for our assumption and the extra bit. So pick out this k to the power of 5, pick out the 4k, and group that bit together. Now what do we have left? Hopefully this is divisible by 5. I see the 4 and the 1 will add together to make a 5 here, and yeah, I can see the others are divisible by 5. So it's 5 lots of k to the 4 plus 2 lots of k cubed plus 2 lots of k plus 1 times 4 is 5, so we need a plus 1 here, so 1 times 5 is 5. Great, so what we have here is this part here is by our assumption, and then we summate this with a multiple of 5. It obviously has a factor of 5 here. So we need to just write a little conclusion here. As we have the summation of two multiples of 5, one by assumption and one by a factor of 5, the summation of these will also be a multiple of 5. So as the summation of two multiples of 5 will also be a multiple of 5. F of k plus 1 is divisible by 5. Okay, so that's still step 3. We still need to do our part 4 conclusion. So that's going to be as we have proven true for n equals 1, and assuming true for n equals k, we have shown true for n equals k plus 1 by induction f of n equals n to the 5 plus 4n is divisible by 5 for n exists in the z plus. I nearly missed that out there. Make sure you don't miss that out because they do deduct marks if you don't include that bit there. Right, okay, part B is show that f of minus x is equal to minus f of x. Okay, so f of minus x is going to be, this part B, is going to be equal to minus x to the power of 5 plus 4 lots of minus x. We can pull this out. We know that this is going to be the same as minus x to the 5 minus 4x. Factorize out the minus, we're going to get minus bracket x to the 5 plus 4x, which is exactly the same as minus 5 minus f of x. Okay. So that's part B done, that's for all natural numbers, so hence part C should follow nice and simply, hence prove that f of n is divisible by 5 for all n exists in the integers. So what we need to do is write a little sentence here. As we know from part A, that f of n is divisible by 5 for all n exists in z plus, then by part B, this is also true for z in the negatives. All we just need to do now is just finish off for the 0 one, because we never actually did the 0 one. F of 0 equals 0 to the 5 plus 4 lots of 0, which is 0. And, well, I suppose technically, that is divisible by 5 by a factor of 0 is divisible by 5. So therefore, we can say that f of n is divisible by 5 for all n exists in the z. Okay, so that was a bit of a different one towards the end there, but 9 marks in total.